Welcome to this walkthrough of problem number 869, Reordered Power of 2. In this problem, we'll explore an interesting challenge involving permutations of digits and powers of 2. By the end of this session, you'll gain insights into different approaches to solve this problem efficiently. Let's dive in. In this problem, we are given a positive integer n and need to determine whether its digits can be reordered to form a power of 2. By rearranging its digits in any order, we aim to find out if the resulting number can be expressed as 2x, where x is a non-negative integer. Some examples of powers of 2 include 1, 2, 4, 8, 16, 32, and so on. The input will be a single integer n, which lies between 1 and 10 to the power of 9. The output is expected to be a Boolean value, true if it is possible to reorder the digits of n to form a power of 2, and false otherwise. For instance, let's consider the example where n is 1. Here, the output would be true because the number 1 itself is a power of 2, specifically 2 0 equals 1. Another example is when n is 10. In this case, the output is false, as the digits of 10 can only be reordered to form 0, 1 or 10, neither of which is a power of 2. This demonstrates that not every integer can be rearranged to satisfy the condition. Now, let's look at another example where n is 46. The output here is true, because the digits of 46 can be rearranged to form 64, which is a power of 2, specifically 2 equals 64. Additionally, the problem comes with a few constraints. The input number n is guaranteed to be a positive integer and can have up to 9 digits. When rearranging the digits, leading zeros are allowed but do not affect the validity of the number. For instance, 0, 1 is equivalent to 1. This flexibility ensures that all possible reorderings are accounted for. We should also consider cases where the input number has repeated digits. For example, if n is 1288, it can be reordered to form 2816, which is a power of 2, specifically 2 11 equals 2816. This highlights the importance of handling repeated digits correctly. To further test the solution, edge cases such as single-digit numbers and large inputs close to 10 to the power of 9 must also be considered. Single-digit numbers are straightforward, as only numbers like 1, 2, 4, and 8 are powers of 2. Larger numbers, on the other hand, require the algorithm to remain efficient despite the increased complexity of possible digit permutations. To tackle this problem, one straightforward approach is to generate all possible permutations of the digits of the given number, n, and then check if any of these permutations form a power of 2. This method, while conceptually simple, involves 3 main steps. First, we generate every possible arrangement of the digits in n. Next, for each permutation, we convert it into an integer and verify if it represents a power of 2. Finally, if we find even one permutation that satisfies this condition, we return true, otherwise, we return false. However, the inefficiency of this approach quickly becomes apparent when we consider the computational complexity. Generating all permutations of the digits involves factorial time complexity, denoted as O, k, where k is the number of digits in n. Additionally, for each permutation, checking if it is a power of 2 requires logarithmic time in relation to the size of the number, leading to significant computational overhead. While this approach works well for smaller inputs, its factorial growth makes it impractical for numbers with many digits, leading us to explore more efficient alternatives. A more efficient solution leverages the concept of digit frequency comparison. Instead of generating all permutations, we recognize that two numbers with identical digit frequencies can be rearranged into one another. This insight allows us to bypass the need for permutations entirely. The strategy is built on 2 key observations. First, the powers of 2 grow exponentially, meaning there are only a limited number of powers of 2 within the range of 32-bit integers, specifically, up to 2 to the power of 30. Second, the digit frequency of a number, which counts how often each digit from 0 to 9 appears, provides a unique fingerprint for the number that is independent of the digit order. Using these insights, the steps become straightforward. We start by calculating the digit frequency of the given number, n. Then, we pre-compute and store the digit frequencies for all powers of 2 up to 2 to the power of 30. Finally, we check if the digit frequency of n matches any of these pre-computed values. The complexity of this approach is significantly reduced. Computing digit frequencies for all relevant powers of 2 is linear with respect to the total number of digits involved, and calculating the digit frequency of n itself is linear in its number of digits. This makes the approach highly efficient and well suited for numbers with many digits. The chosen strategy for this problem is the digit frequency comparison approach, and it was selected due to its substantial efficiency improvements over the brute force method. While generating permutations involves factorial growth and quickly becomes computationally expensive, the digit frequency method eliminates this inefficiency by focusing on the unique property of digit frequencies. The aha moment here is recognizing that matching digit frequencies is sufficient to determine if two numbers can be reordered into each other. This eliminates the need to explicitly generate and test permutations, reducing the problem to a manageable computation. Although this approach requires pre-computing and storing digit frequencies for powers of 2, the limited range up to 2 to the power of 30 ensures that this overhead remains negligible. In summary, the brute force approach, while simple, is highly inefficient for larger numbers due to the factorial growth of permutations. By contrast, the digit frequency comparison method is scalable, efficient, and computationally lightweight, making it the clear choice for solving this problem. Pre-computing the digit frequencies of powers of 2 allows us to achieve an optimized solution without sacrificing correctness. To solve this problem, we start by understanding the core requirement. Given a number n, we need to determine if any permutation of its digits forms a power of 2. For example, with n equals 46, the possible permutations of its digits are 46 and 64. Since 64 is a power of 2, we return true. A brute force approach to solving this involves several steps. First, we convert the number n into a string. This conversion allows us to easily manipulate its digits as individual characters. For instance, when n equals 46, we convert it into the string 46. Next, we need to generate all possible permutations of these digits. This can be achieved using a permutation generating method such as itertools.permutations in Python. Once we have the permutations, we treat them as integers and discard any invalid results, such as those with leading zeros. For example, for n equals 46, the valid permutations are 46 and 64. After generating the permutations, the next step is to pre-compute all the powers of 2 that are less than or equal to the largest number that can be formed by the digits of n. This ensures that we have a list of potential matches ready for quick comparison. For example, if n equals 46, the largest number we can form from its digits is 64. Therefore, we pre-compute powers of 2 up to 64, which gives us the list 1, 2, 4, 8, 16, 32, 64. With this pre-computed list, we now iterate through each permutation of the digits of n and check if it exists in our list of powers of 2. If a match is found, we return true. If no matches are found after examining all permutations, we return false. We also need to handle edge cases, such as when n is a single digit. In such cases, we can directly check if the digit itself is a power of 2. Additionally, we must carefully handle numbers with repeated digits, such as 112, to avoid redundant calculations. Now, let's discuss some key insights about this approach. Permutations are crucial because they allow us to consider all possible digit arrangements of n, ensuring that no valid combination is missed. Pre-computing the powers of 2 is another key optimization. Instead of recalculating powers of 2 repeatedly for each permutation, we compute them once and use a set for efficient lookups, which allows us to check for matches in constant time. Another important detail is handling leading zeros in permutations. By discarding numbers with leading zeros, we ensure that only valid integers are considered. From a data structure perspective, we use a string to store the digits of n for generating permutations, a set to store the pre-computed powers of 2 for quick lookups, and optionally, a list to temporarily store permutations before filtering out invalid ones. These choices optimize both the clarity and efficiency of our algorithm. Let's analyze the complexity of this brute force approach. The time complexity is driven primarily by the generation of permutations, which takes k, where k is the number of digits in n. Checking each permutation against the pre-computed powers of 2 involves set lookups, which are 1 on average. This makes the total time complexity approximately k. For space complexity, storing all permutations requires k space. Additionally, pre-computing the powers of 2 requires space proportional to the number of powers up to the largest possible number formed by the digits of n, which is O log max _ digit _ number. To optimize this algorithm further, we can avoid generating all permutations by using the frequency count of digits. For each power of 2, we can compare its digit frequency with the digit frequency of n using tools like collections at counter. This eliminates the need to explicitly generate permutations. For smaller values of n, we can also restrict computations by directly comparing against a subset of pre-computed powers of 2. Let's walk through an example to see the algorithm in action. Consider the input n equals 46. First, we convert n to a string, resulting in 46. Next, we generate all permutations of its digits, which are 46 foot, 64. Then, we pre-compute the powers of 2 up to the largest number that can be formed by the digits of n. Here, the largest number is 64, so the pre-computed powers of 2 are 1, 2, 4, 8, 16, 32, 64. Now, we check each permutation. The first permutation, 46, is not a power of 2, but the second permutation, 64, is a power of 2. Since we found a valid match, the result is true. For an edge case, let's consider n equals 1. Since n consists of a single digit, we directly check if it is a power of 2. Since 1 is a power of 2, the result is also true for this case. Now, let's examine another edge case where n equals 10. First, we generate the permutations of its digits, 10 and 01. Next, we pre-compute the powers of 2 that are less than or equal to the largest number that can be formed by the digits of n. The largest number here is 10, so the pre-computed powers of 2 are 1, 2, 4, 8. Checking the permutations, we find that 10 is not a power of 2. The second permutation, 01, is invalid because it contains a leading 0, so we discard it. Since none of the valid permutations match a power of 2, the result is false. This example highlights the importance of handling leading zeros and shows how the algorithm gracefully handles scenarios where no valid permutations exist. The problem requires determining if the digits of a given number can be reordered to form a power of 2. Let's walk through the solution line by line. First, we import the permutations function from Python's itertools module. This function will help generate all possible rearrangements of the digits of the input number. The solution is encapsulated within the reordered power of 2 method of the solution class. The input n is converted to a string n_str to facilitate digit manipulation. Next, we use the permutations function to generate all possible orderings of the digits. However, since leading zeros are not valid, e.g., 012 is not a valid number, we skip any permutation where the first digit is 0. Each valid permutation is then converted back into an integer number by joining the digits and converting the result to an integer. The next step is to check if this number is a power of 2. For this, we use the bitwise property of powers of 2. A number is a power of 2 if number and number 1 equals 0. This condition ensures that there is only one bit in the binary representation of the number. If we find a permutation that satisfies the power of 2 condition, we immediately return true. If no such permutation exists, the function returns false after exhausting all possibilities. This approach ensures a comprehensive search of all permutations while efficiently checking for powers of 2 using bitwise operations. This is the Java implementation of the reordered power of 2 problem. The logic mirrors the Python solution, checking if the digits of a number can be reordered to form a power of 2. Key differences include Java's use of type declarations, character arrays for digit manipulation, and the arrays utility class for sorting and comparison. The solution iterates through all powers of 2 up to 10 to the power of 9, ensuring efficiency and correctness. To solve the problem, we start with the input n equals 1. First, we convert the integer n into a string, giving us n_str equals 1. This makes it easier to work with its digits. Next, we calculate all the permutations of the digits in n_str using the itertools.permutations function. Since there's only one digit in this case, the only possible permutation is 1, Now, we check each permutation. For the permutation 1, we skip the leading zero check because the first digit is not 0. We then convert this permutation back into an integer, which results in number equals 1. To determine if number is a power of 2, we use a bitwise condition, 1 and 1 to 1 equals 0. This evaluates to true, so we conclude that 1 is indeed a power of 2. Finally, we return true as the result for this input. The output for the first example is true. Now, let's consider the second example with the input n equals 10. Again, we start by converting the integer n into a string, resulting in n_str equals 10. Next, we generate all permutations of the digits in n_str. The possible permutations are 1, 0, 0, 1. For the first permutation, 1, 0, we skip the leading zero check because the first digit is not 0. We then convert it to an integer, giving us number equals 10. Checking whether 10 is a power of 2 using the bitwise condition, 10 and 10 to 1 equals 0, we find that it evaluates to false. For the second permutation, 0, 1, we skip this permutation entirely because the first digit is 0, which makes it invalid due to leading zeros. Since there are no other permutations left to check, we proceed to the next step. At this point, we've checked all permutations of the digits in n equals 10 and found that none of them represent a power of 2. As a result, we return false for this input. Now, let's move on to the third example, where n equals 46. First, we convert the input into a string, resulting in n_str equals 46. Then, we generate all possible permutations of the digits in n_str. The permutations are 4, 6, 6, 4. These represent the two ways we can rearrange the digits of 46. With the permutations ready, we can now check each one to see if it forms a valid number that is a power of 2. For the first permutation, 4, 6, we skip the leading zero check since the first digit is not 0. We convert the permutation into an integer, resulting in number equals 46. Checking whether 46 is a power of 2 using the bitwise condition, 46 and 46 to 1 equals 0, we find that it evaluates to false. Next, we examine the second permutation, 6, 4. Again, we skip the leading zero check because the first digit is not 0. Converting this permutation to an integer gives number equals 64. Checking whether 64 is a power of 2 using 64 and 64 to 1 equals 0, we find that this condition evaluates to true. Since we've found a valid permutation that is a power of 2, we return true as the result for this input. To analyze the time complexity of this solution, we begin by examining the generation of permutations. If the number of digits in the input number n is denoted as d, the permutations function generates all possible arrangements of these d digits, resulting in a total of d permutations. For each permutation, we perform certain operations such as converting the tuple to a string, then to an integer, and finally checking if it is a power of 2. The conversion and parsing steps collectively require O(d) time, while the power of 2 check is a constant time operation, O(1). When we multiply this processing time, O(d), by the total number of permutations, d, we get an overall complexity of O(d). *d. Additionally, the check for leading zeros is performed in constant time and does not impact the overall complexity. Thus, the total time complexity of the solution is O(d). *d, where d is the number of digits in the input number n. Now, let's discuss the space complexity. The primary factor here is the memory used during the computation of permutations. The permutations function generates these arrangements as an iterator, meaning that only the current tuple is held in memory at any given time. This results in a space requirement of O(d) for storing the current tuple. Additionally, temporary memory is allocated when converting tuples to strings and subsequently to integers, which also requires O(d) space per operation. The function itself does not involve recursion or deeply nested calls, so the function call stack usage is negligible, contributing only O(1) space. When we combine these factors, the overall space complexity of the solution is O(d), which is determined by the storage requirement for intermediate computations like string conversions and the current permutation. Let's consider how this optimized approach compares to alternative methods. A brute force approach might attempt to generate all possible integers up to a certain limit, such as the largest number with d digits, and check each one to see if it is both a permutation of n and a power of 2. This would be extremely inefficient, as generating all numbers up to 10 to the power of d would take 10 to the power of d time. Additionally, verifying if each number is a permutation of n would take d operations, and checking if it is a power of 2 would take 1. The overall complexity in this case would be significantly worse than d. *d. A more efficient alternative is the pre-computation approach, where we calculate all powers of 2 within the range of integers that have up to d digits. For a 32-bit integer, this corresponds to powers of 2 from 2 to the power of 0 to 2 to the power of 30. We then compare the digit frequency of n to the digit frequencies of these pre-computed powers of 2. This approach reduces the complexity to k*d, where k is the number of pre-computed powers of 2, approximately 30. This optimized method is far more efficient than the brute force approach. Finally, let's break down the best, average, and worst-case scenarios for this solution. In the best case, the very first permutation generated is a valid power of 2, resulting in a time complexity of d, as only one permutation needs to be processed. On average, the solution will need to check many permutations before finding a valid power of 2, and the time complexity will approach d. *d. In the worst case, every permutation is checked, and none of them corresponds to a power of 2. Here, the time complexity is also d. *d. Summarizing the overall performance, the time complexity of the solution is d. *d, while the space complexity remains d. This encapsulates the computational requirements of the algorithm across all scenarios. When working on this problem, there are a few common mistakes to watch out for. First, not accounting for leading zeros in permutations can cause issues. For example, if you generate the permutation 012, it might be interpreted as the number 12, but leading zeros are not valid in numerical comparisons. This can lead to incorrect results, so it's essential to filter out permutations with leading zeros. Another mistake is inefficient permutation generation. If you generate all permutations blindly without using constraints, you can waste a lot of computational resources. A better approach is to use pruning techniques or stop the generation process as soon as a valid power of 2 is found. Finally, misinterpreting the problem constraints can lead to missed edge cases. For instance, assuming the input will always be small or simple can cause failures when dealing with large numbers or inputs with repeated digits. Carefully reading the constraints and testing for edge conditions, such as n equals 1, n equals 0, or numbers with duplicate digits, is critical for creating a robust solution. Another common issue is checking only a subset of powers of 2. Some solutions set an arbitrary limit on the powers of 2 they consider, which can fail for larger inputs. Instead, you should dynamically generate all powers of 2 within the range of possible permutations for the given input. Additionally, ignoring time complexity is a major pitfall when using brute force approaches. Generating all permutations has factorial growth, which can quickly lead to a time limit exceeded error, especially for larger inputs. A more efficient approach is to pre-compute all possible powers of 2 and compare their sorted digit counts to the input, rather than generating and testing every permutation. This not only reduces computational overhead but also ensures scalability for larger test cases. From an interview perspective, this problem is a great opportunity to demonstrate your ability to manipulate digits effectively. Many variations of this problem involve sorting, counting, or rearranging digits, so it's helpful to practice techniques like using frequency arrays or sorting digits. For larger inputs, brute force solutions simply won't scale, so discussing pre-computation and optimizing comparisons can highlight your ability to handle complex scenarios. It's also important to communicate trade-offs. For instance, pre-computing powers of 2 can save runtime but may increase memory usage, and explaining how you balance these trade-offs can impress your interviewer. Finally, edge cases are always a focus in interviews, so make sure to plan for situations like invalid inputs, zeros, or numbers with repeated or missing digits. Being thorough in your approach will leave a strong impression. This problem shares similarities with several other LeetCode problems that you might find useful to explore. First, LeetCode 869 itself focuses on rearranging digits to form a power of 2, which makes it the most directly related. LeetCode 46, which deals with generating all permutations, can help you understand the underlying mechanics of permutation generation. LeetCode 49, group anagrams, involves comparing character frequencies, a concept that's closely tied to digit frequency comparisons in this problem. Finally, LeetCode 202, happy number, is another problem that utilizes digit-based transformations, which can help you develop a strong foundation in digit manipulation. The key takeaways here are that scalability is critical, factorial growth makes brute force impractical for larger numbers, so digit frequency comparisons are more efficient. Pre-computing powers of 2 and storing their sorted digits can significantly improve lookup times. And always clarify constraints to ensure your solution addresses the full range of possible inputs effectively. Digit-based techniques, like sorting or using frequency arrays, are versatile tools that you can apply to many problems beyond this one. Great job making it to the end. We reviewed the problem reordered power of 2, discussed efficient approaches, and highlighted key takeaways. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. Keep up the great work and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!